In this video, I'm going to show you how to derive the formula for the differential scattering cross-section in terms of the Feynman amplitude for types of scattering events which consist of two incoming particles scattering off each other into some number of outgoing particles. It's one of the most important formulas in quantum field theory because it's one of the most useful ways to connect quantum field theory to actually experimentally observed quantities. The formula that I'm going to derive for you specifically relates the Feynman amplitude to the scattering cross-sections. The Feynman amplitude is what's given directly through the application of Feynman rules, which come from quantum field theory. So if you analyze your quantum field theory to get the Feynman rules, then through this formula, that's all you need to get an actually experimentally observable quantity, the differential scattering cross-section. So here follows the math section where I give all the rigorous details. In quantum field theory, it is a bit of a lengthy process to go from the classical action of a given quantum field theory to actual physical predictions like scattering cross-sections and decay rates. There are two commonly used ways. The first is the operator method and the second is the path integral method, which basically just differ in how the scattering matrix is computed. However, beyond the scattering matrix computation, the procedure is the same. They both yield equivalent scattering matrices and therefore the same formulas must be used to obtain physical information from the scattering matrix. In this video, I will derive the formula for the differential scattering cross-section in terms of the scattering matrix, more specifically a part of the scattering matrix called the Feynman amplitude. This is one of the most important formulas relating the scattering matrix to a physically measurable quantity. The specific derivation here concerns two particles scattering to n particles. This is by far the most commonly encountered type of scattering cross-section in quantum field theory. This is the case basically because scattering experiments usually consist of two colliding beams. Before I do this derivation, however, I will give a rather detailed introduction to the concept of a differential scattering cross-section. This is important because understanding this quantity is central to nuclear and particle physics, and many students walk into quantum field theory class not really understanding it. If you already are very familiar with scattering cross-sections, then you can skip straight to the calculation. Consider for a moment a thin foil, specifically one thin enough for none of the particles in it to be overlapping from a head-on view, or perhaps a diffuse beam pulse of particles if you don't want to select the target reference frame. Given that we are taking the targets to be very diffuse, the probability of a given particle scattering is simply the area of the target covered by particles divided by the total target area, where the total area covered by particles is simply the area covered by one particle times the number of particles. The amount of area covered by one particle is called the total scattering cross-section of the particle. It is the magnitude of the area that the projectile must hit in order to scatter off of a given target particle in any direction at all. It is basically the size of the target particle. However, one may ask for something more detailed. One might only have a detector covering a certain solid angle on the sphere surrounding the scattering event. In this case, the total scattering cross-section isn't very useful. Instead, one would prefer to know the magnitude of the area on the target particle that must be hit by the projectile for it to scatter into the particular solid angle covered by the detector. This way, one can multiply that by the number of particles on the target, and then divide it by the target area to get a scattering probability specifically for projectile particles scattering into the detector subtending that particular solid angle. One can develop a quantity called a differential scattering cross-section that can give you this for an arbitrary solid angle. One simply integrates the differential scattering cross-section over the particular solid angle in question, and it spits out the required area. Obviously, if one integrates over a solid angle covering the whole sphere, then one obtains the total scattering cross-section. It is worth noting that in such experiments, either the target consists of only one particle at a time, e.g. another accelerator beam, or the target has a small width and height compared to the distance to the detector, so the differences in angle between the various particles in the target and the detector are negligible. Therefore, the cross-section for a given solid angle can be safely taken to be the same for all particles in the target. One can then add important layers of complexity to these concepts of total and differential scattering cross-sections that make them actually especially useful in real nuclear and particle physics experiments. First, quantum particles don't actually have well-defined areas, yet the above discussion treated particles as though they did, like hard spheres. While quantum particles don't have well-defined areas, they do still have some reliable tendency to scatter particles off into some solid angle, a tendency that varies depending on the type of particle composing the target and the incident beam. Therefore, they must have some effective area. This is how total and differential scattering cross-sections are thought of in real particle physics. The other important layer of complexity that must be added on is that we can consider the possibility of scattering cross-sections for particular types of scattering, not just for scattering at all. When particles collide, merely bouncing off of each other is just one possibility. They may transmute into other types of particles and different numbers of them. One can write scattering cross-sections not just for scattering into a particular solid angle, but for a particular type of scattering to occur, and then for the output particles of that particular scattering to fall in some particular set of solid angles, and output momentum magnitude ranges, which will be discussed shortly, where one can consider separate solid angles for each output particle. Even if the target and projectile particles aren't varied, the effective area associated with the scattering to yield a particular set of particle outputs will change depending on which output set, particle reaction, you are considering. And I say particle reaction here is interchangeable with output set because different particle reactions are needed to yield these different output sets. So when I say that it changes based on which output set you're considering, I'm basically just saying the scattering cross-section changes based on which reaction you're considering, even if you're considering scattering of the same types of particles. In addition to all of this, scattering cross-sections are also usually written for a particular range of output momentum magnitudes, in addition to the already discussed momentum vector directions given by the solid angle dependencies. Differential scattering cross-sections are usually written for arbitrary differential output momentum intervals. Therefore, to get the effective cross-sectional area for a scattering process to yield output particles in a particular set of solid angles, one for each particle, and within a particular set of output momentum ranges, again one for each particle, one must not just integrate the differential scattering cross-section over the necessary solid angles, but also the desired output momentum intervals. The cross-section is also usually a function of the input momenta, but only specific input momenta, not ranges, because the scattering event does not affect the momenta that the scattering particles come in with. That is selected by the experimenter. So far, I have defined the scattering cross-section as the effective cross-sectional area needed to yield the observed scattering probabilities and rates. This can be reworded in a way that is perhaps less useful for conceptualization, but that is better for computation. To do this concisely, we must first define a bunch of new notation. I'll use this symbol to denote the differential scattering cross-section, this one to denote the total scattering cross-section, this to denote the target area. This little v will denote the beam velocity. Rho b will denote the number density of the beam. Rho t, the number density of the target. And rho b times v, of course, would just then be the flux. Nb will denote the number of particles in the beam and is unsurprisingly given by rho b times the velocity times time times the area. The area times the velocity times the time is the volume of the beam, and then we're multiplying it by the density. Then the number of particles in the target, denoted Nt, is just the density of the target times its volume. Although I describe the target area as very thin, we're still discussing its volume. This symbol will be used to denote the differential transition rate per unit volume, where for these derivatives to make sense, this would have to be the transition probability, and that's the notation we will use for it. The differential in the above line, this one, references the outgoing momentum space volume differentials that we will see it depends on. These differentials can be written in spherical coordinates, which breaks them apart into solid angle differentials and momentum magnitude differentials. These are the differentials that we were talking about above. With these definitions, we can work out a starting formula for the scattering cross-section. The easiest way to do this is to start with the total cross-section and then write out the differential version afterwards. First, given that the total cross-section is the effective cross-sectional area of the particle for a given scattering process, we can write this. The chance of a scattering event is the number of particles in the target times the area of those particles over the area of the target. Therefore, the number of such scattering events is simply this times the number of projectiles. We can then solve that for sigma, which gets us here, and then substitute those formulas for NB and NT that we had from above. That gets us ultimately to here. So we have that the scattering cross-section is the transition rate per unit volume over number density of target times 1 over the incident flux. So this is the rewording I was talking about. And if we want to take the differential version, well, we just take the differential transition rate per unit volume, and that's simply this. With this starting formula for the differential scattering cross-section established, we can now proceed through the derivation of the explicit formula for the case of two-particle scattering in quantum field theory. I will explicitly derive the formula only for two bosons scattering to n bosons. However, I will give the results for the cases involving just fermions both in the input set and in the output set, and for a mixture of fermions and bosons in the input set and the output set. The only reason why anything changes when one goes from considering bosons to considering fermions, or vice versa, is that bosonic and fermionic states are traditionally normalized differently. The standard normalizations for one-particle fermionic and bosonic states are like this. You see that we're not choosing these same factors, and that is just a standard convention. We've got this factor of 2 here, and then we've got this factor of 1 over m here, which are the differences between the two. From the identity operator, we can see what momentum space volume integration measure is consistent with these choices, these integration measures here. In a scattering calculation like this, we are considering two particles, each with a localized bell curve-like distribution in momentum space, and therefore in position space, hitting each other and scattering off to yield a set of output particles with momentum vectors in particular differential ranges, as described above. The process of deriving the scattering cross-section for this type of experiment will consist of deriving an expression for this quantity, the number density of the target, and the incident flux, in terms of the states in question and associated quantities. For most of the problem, the part dedicated to computing this, there is no gain associated with specializing to a particular reference frame. However, the above formula for the differential scattering cross-section mostly assumes the rest frame of the target, and towards the end of the calculation, when we compute the incident flux and the target number density, we will again assume this reference frame. Despite this frame selection, the final answer will be valid for all collinear reference frames. I will explain this more when we get there. We will now construct this differential transition rate. Given the normalizations provided above, such a localized one-particle state can be written like this, where this f function consists of a localized peak at some location in momentum space. Therefore, the two-particle initial state we desire is simply given by this, where we have two of these Fourier coefficients and a two-particle momentum state. We are considering the scattering of this state into a particular final state of this form, with the final particles exiting with momentum vectors localized to differential-sized momentum intervals, like this, again properly normalized. The probability amplitude for the initial state to scatter into some final state of this form is given by this matrix element of the S operator, where the S operator time evolves the asymptotic initial state to asymptotic output times, and then we take the inner product with the final state to see what the probability amplitude is that it is in the final state that we've selected. We are in the interaction picture here, so that explanation makes sense. If we were in the Heisenberg picture, it wouldn't, because states don't time evolve on the Heisenberg picture. For more on this, see my video on the scattering operator. The momentum space probability distribution is simply the modulus squared of the probability amplitude times the differential range of the momentum, the output momentum, because that's not integrated over, and we're dealing with a continuum, so we need the properly normalized differentials to actually get the probability. Then we could integrate over this to get the probability that we're scattering into some range of momentum, where in this formula, because we are in natural units, these two things are directly equal to each other instead of having that factor of h bar relating them. Because of their equivalence, these two quantities will be used interchangeably in the notation. Now let's break the S operator into a forward scattering part and a transition part. I will explain what these are next. So we have S is equal to the identity plus some transition part, where I is the identity operator and t is called the transition operator. Now let's substitute this into the matrix element. It gets us here. Now I will explain what the forward scattering and transition parts are. The forward scattering part of the matrix element, this part here, which came from the identity, is just a probability amplitude that the initial state is the final state and no scattering occurs, but instead the particles in the initial state enter and exit without changing state at the interaction site. For some reason this is traditionally called forward scattering, even though it is the absence of scattering. The second term describes actual scattering. It gives the probability amplitude that the particle in the initial state scatters into the final state. This quantity is called the transition amplitude, and as the name implies, it is the probability amplitude that scattering induces the input particles to transition to a new state, f. The transition probability, of course, is just the modulus squared of this, times the appropriate momentum differentials for the same reason as when we put them in this formula here for the probability altogether. Because we are interested in the differential scattering cross-section, actual scattering, not forward scattering, we will be dealing exclusively with this quantity here. It, of course, is the transition probability, so if you want the transition rate per unit volume, this quantity here, we're going to have to be dealing with that. We're not interested in forward scattering here. In our effort to compute this, the next step is to insert the formula we wrote down for the initial state into this quantity. Remember, the initial state was given by this formula. If we insert it, then we find ourselves with this insane formula, and then simplifying a little bit, which just in this case consisted of moving some of these factors around, gets us to this. We ultimately seek this quantity, and the next step to computing it is to compute the momentum integrals. I will have to make some new definitions to do this, and also carry out some more manipulations before we ultimately get to doing it. The definitions I need to make are basically establishing notation for the Fourier transforms of the momentum space Fourier coefficients, and I'm just going to call them f tilde of x. These satisfy the Klein-Gordon equation because the phases used in the Fourier transform are plane wave solutions of the Klein-Gordon equation. This will be very important later on after we finished computing this and we want to find the incident flux and target particle density. We're not just going to ignore that. It's not just a chance fact that we're not going to take advantage of. I'll give a brief summary here of why it is important. For both of these quantities, we need the number density of the particles, and because they satisfy the Klein-Gordon equation, the time component of the Klein-Gordon Noether current gives us these number densities. Now we must consider momentum conservation, because this is what will allow us to do the momentum integral. This can be imposed with a delta function, thus allowing the transition amplitude to be written as the product of a delta function and some other quantity, usually called the Feynman amplitude. The usual definition is this: we pull out a factor of a delta function and a factor of 2 pi to the fourth, and we use this factor as the defining difference between this quantity, which we're already familiar with, and this one, which we're going to ultimately write the scattering cross-section in terms of. It turns out this is the quantity that is directly given by the Feynman rules, which is why it's useful to us here. Kf in this formula is the sum of all final 4 momenta. I can't denote it 1 through whatever, because we're leaving the number of different output particles arbitrary. Inserting this gets us here, and then we can take advantage of that identity with delta functions, where you have a function multiplying it, and it sets the value of the function factor on the delta function, except this time it's another delta function that's multiplying it, so we get this funky result, and it's this delta function here that's going to help us out. So plugging that in gives us this, and in order to actually allow this delta function to help us out, we need to write out its definition and substitute that in. Now what we see with this factor in here, these integrals are just the Fourier transform of these factors here, or at least they would be if we didn't also have these ones. So we've got some work to do, but the ultimate goal is to rewrite this such that these momentum integrals just amount to doing Fourier transforms of these various factors. So what can we do about that? Well, we need to remember the form of these two factors. They consist of bell curves localized around the averages, which I'll denote with bars. This means that when placed under the integral, this is actually approximately just equal to that, because it'll basically zero the integrand out anywhere except right at the spike. It's very similar to a delta function. It's approximately like that. Additionally, while the k tildes are separate integration variables, the functions f1 and f2 are the same regardless of which integration variables they depend on. So their localized peaks lie in the same places in momentum space. So the complete set of approximate equalities is actually this, where if it isn't clear, we are taking the average momentum to be constants and not other integration variables. Basically, we were replacing the integration variables in the matrix elements with their constant average values because f1 and f2 behave approximately like delta functions. Inserting this gives this result. Similar logic allows us to replace the variables in this delta function with their averages. Now we're finally just left with Fourier transforms of the f functions because of this phase factor here. If you remember back to how we got here by inserting this delta function formula, and the delta functions ultimately got there from momentum conservation and transitioning to writing things in terms of the Feynman amplitude, and you remember. So we're integrating over a delta function, and that's imposing momentum conservation, this relation, but it leaves behind this factor, this energy time factor, because we're integrating only over the three momentum variables and not the energy variables. But this momentum conservation through the relation to energy ultimately gives us energy conservation too, because all we've got here is kinetic energy. It's a free particle scattering, and this being true turns that phase to 1, so we get this, which gets us closer to our ultimate goal. In fact, we've got this four-dimensional volume integration, so if we just take this derivative, then we arrive at this quantity for the transition rate per unit volume, which is exactly what we're looking for. Now on to the other two quantities we need, the incident flux and the target density. For the rest of the calculation, I will take the rest frame of the particles of type 2. However, at the very end, the result will be valid for any collinear frame. I will show that this is the case. In this frame, the particles of type 2 compose the stationary target, and the particles of type 1 compose the incident beam. That is the way I'm going to make the identification. As established above, the differential scattering cross-section is this. We now have this quantity. We need these two quantities. It is clear that selecting this particular frame at this point will only affect the denominator because we've already calculated this. To compute the number density of the target and the incident flux, we must recall a couple of things about this f1 tilde and f2 tilde functions. First, they describe the position space spread of the incident beam particles and the target particles, and they satisfy the Klein-Gordon equation. This means that we can use the time component of the Klein-Gordon field current to get the number density of both types of particles. This directly yields one of the things we need, the target number density, and indirectly yields the other, the incident flux. So these are the currents we're dealing with, and we need the time components to get the densities. We're going to deal with the particles of type 2 first, so the ones that we just need the density for, the number density for. Then we'll deal with the number density of particles of type 1, and we'll multiply it by the velocity to get the flux, as per the formula I gave at the beginning. Taking the time component gives us this formula for the number density that we need. Now we can remember that f of x is given by this quantity. Given that f2 of k consists of a localized peak centered around k2 average, the Fourier transform will be that of the delta function times a slowly varying function of x, meaning a three-dimensional position, not time, which gets us to this. Inserting that into the formula for the number density gives us this result, ultimately through the algebra that I've shown. So we have our final result. Now we can compute the flux of particles of type 1. The calculation of the number density goes exactly the same because it's all the same formulas, all the same logic, and we have this. Then we can work out the velocity and multiply it by this to get the flux. The standard relativistic relation can be solved for the velocity. I've written out all the algebra steps in case it's not obvious, and ultimately multiplying it cancels that factor of omega bar, which you saw there. So we get this result for the flux. We now have everything we need to write out the differential scattering cross-section. Remember this formula? We've calculated this. We just got done calculating this and then this. So now inserting these values for those quantities gets us here. Then we notice that we have these factors of the modulus squared of the Fourier transform of these f functions, but they exactly cancel, leaving us with something completely independent of them. And that gets us here. In order to get it into standard form, we need to rewrite the denominator a little bit. These are the algebra steps. It's pretty straightforward. We have arrived at a result that looks valid and Lorentz invariant, and therefore presumably could be applied for the case of any reference frame. But this is not true. The differential scattering cross-section is exactly that, a cross-section, meaning an area. It must therefore transform like an area under general Lorentz transformations. Every part of equation A except for the denominator is clearly Lorentz invariant, and no particular inertial reference frame or class of inertial reference frames is used in the derivation. By every part except the denominator, I basically mean this quantity, the differential transition rate per unit volume. The denominator must therefore transform like an inverse area under Lorentz transformations. The denominator and the scattering cross-section would therefore be invariant under Lorentz transformations perpendicular to that area, i.e. collinear Lorentz transformations, but not all Lorentz transformations. Because of this, one finds that the denominator cannot be manipulated into a Lorentz invariant form if one is not working in some collinear frame. Therefore, inserting this final result for the denominator yields a formula for the differential scattering cross-section that is valid in all collinear reference frames, but not just general ones. The differential cross-section for just boson external legs is therefore this, which we can rewrite in terms of this symbol as is usually done. And that gives us this. As I said previously, MFI is called the Feynman amplitude, and it's what's given directly by the Feynman rules, which is why the formula in this form is particularly useful. We can just substitute the results of the Feynman rules directly in, and then the Feynman rules come out of quantum field theories. That's ultimately how we're going from quantum field theory to a differential scattering cross-section. This calculation can be repeated with the fermion normalizations given above for the case of scattering fermions or a combination of fermions and bosons scattering off of each other and being present in the output. One gets the following results. For the case where fermion external legs are also present and 0 of the 2 incoming particles are fermions, we have this result. If one of the incoming particles is a fermion instead of a boson, but the other one's left a boson, then we have this formula. For the case of both incoming being fermions, but the output also including bosons, we have this one, and then of course we just leave off the boson factor if we only have fermions going out. That's the case for all of these, where these NF and NB for all of the above are the number of fermions and number of bosons respectively. So that completes the calculation. That is how you derive the formula for the differential scattering cross-section in terms of the scattering matrix, or the Feynman amplitude part of it, and it's a very important formula. It's very cool. So that concludes the math section. You have now seen a comprehensive, detailed derivation of the differential scattering cross-section in terms of the Feynman amplitude for 2 incoming particles scattering to some number of outgoing particles. I hope this video helped deepen your knowledge of quantum field theory. I hope you found it fun. If you did, please give it a thumbs up, and don't forget to subscribe.